Heavenly Father, thank you for this day. Thank you for your love. And thank you for what you have in store for us, even this weekend and next week. It's almost looking like a blur. So many things so many things happening. But you promised to lead us through places just like this, and we can be at rest, and we can trust. And if we can't trust, you're good to endeavor to help us. And so do that, Father. Help us as a class. Because everybody in here, except me, has other classes they got to deal with. But you can help us as a body to learn to trust and to allow you to take the weight. And I pray you'd help us all in that regard. In Jesus' name, amen. Okay, so I don't know if you have seen the study guide. So this time we're not asking you to write out questions and answer them. A good portion of that are just a rehash of the notes that I don't know that anybody in this class takes notes, but if you did, you'd have quite a bit in your notes. But if you didn't, then they were passed out, and you have those follow along sheets that you passed out with the lecture. So those are there. And so I just got that done last night. I hope to have it done earlier, but I just couldn't get to it. So if you have any questions about that, you can contact me. We're going to have class on Monday because that's our last day class. And so I'm going to go over this one, the one you turned in 16, I guess. So I'm going to go over 16 on Monday. I'm not sure that we're going to have a whole bunch. I don't think. I have 4 sections in this part: thunderstorms, lightning, tornadoes, and hurricanes. I'm not sure if we're going to get to the last 2. So I'm not going to. We might punt on that because I just don't have. Let me do this. These test questions that I turn back. If you turn them in to me, I'm turning them back to you. If you turn them in late, then I'm not turning them back to you because I have a pile to grade for the async class and the ones that might not have turned them in on time. So this is air masses. I'll go over this briefly. So what are the characteristic properties of an air mass? There are 2: temperature and moisture. Only 2. What are the 5 basic types of air masses? Many of you, on page 579, you read down on the little part that says source regions, right here, and you read down and it says air masses are classified according to their source region. Okay, polar, Arctic, tropical, continental, maritime. But in this basic types, so this was a key. It says they were classified according to their region, but in the bottom paragraph of this source region says the basic types of air masses according to this scheme of classification are continental polar, continental Arctic, continental tropical, maritime polar, maritime tropic. So I was looking for that. That's what I was looking for. I think I gave a point or 2. If you didn't do it, I didn't count it totally off. But that was what I'm looking for. These were what I'm looking for. Those are the basic types. And the only thing you can find basic types in is that last little paragraph. This is basic types. So, if I'm wanting you to get something specific, like characteristic properties. Characteristic properties. There are lots of things that people have put, but the characteristic properties, there are 2 of them. It says characteristic properties, and they were there. Like these are here. So, and the next couple are just absolutely what it says in the book. In the winter, I describe weather associated with continental polar air mass. In the winter and summer. In the winter, it brings clear skies and cold weather. In the summer, it brings a few days of cooling relief. Cool, dry air. And would this be most welcome to the U.S. in the summer? And if you added something when it's hot and humid, if you add something to these things, and some of you have, you'll see little pluses by what you write, and I see a +1 or a +2 or something like that. That's when I see you step a little bit farther, and so I give you credit for that. So some of you have done really well with that. How many points were that? 39. Okay. Some people got like 45, 46 points on this because they did interesting. They just add things, not just fluff, but things that bear, like say in the summer when it's hot and humid. Well, that's not a big deal, but if you inserted that, you're processing a little better. So it's not required to get full credit to do that, but if you got it, then you got it. So what are some characteristics of maritime tropical air mass? The characteristics are they're warm, moisture-laden, and usually unstable air. That's page 590. It starts on the end of 579, right at the bottom, and then you turn over, and it says, as you might expect, these air masses are warm, moisture-laden, and usually unstable. That's the maritime tropical. So that is where that is. And so, what are the source regions? Gulf of Mexico, Caribbean, and the adjacent Atlantic Ocean. If you just said Atlantic Ocean, that wasn't true. It's adjacent, because the Atlantic Ocean goes all the way up the coast. It can be the North Atlantic. Well, it's not the North Atlantic. The North Atlantic isn't going to get you any kind of warm, tropical, maritime air mass like that. It's the maritime tropical. It's got to be south, so it would be adjacent. The Atlantic Ocean adjacent to the Caribbean Sea and the Gulf of Mexico, right down there. That's where it would be. The maritime polar are the North Pacific and the North Atlantic. The North Pacific comes out of Siberia, across the Pacific Ocean, and it does that, and then the North Atlantic as well. You said something about them being unstable or a nor'easter. I gave you extra credit. And I gave you extra credit for more than just what I put down, but that's what I was, if somebody put that down, I wanted to make it up for myself. So, this is probably important to know. Describe the weather along a cold front where very warm, moist air is being displaced. So you've got a cold front, and it's coming into a warm front. And so the cold front coming in, and this warm front just amble it along, and the cold front hits a warm front. It kicks it up steep. So what can you expect if a cold front kicks this warm front up really steep? Well, it's going to rain really heavy, going to be strong wind gusts, but it's going to be a short duration. It's not a long time. You're not going to have sudden down. We're going to have downpours and strong wind gusts for days or many, many hours. It's usually a short duration. It hits hard because this thing kicks this stuff up steep. So this moisture-laden warm air is kicked up by this cold front really fast, and so it's moisture-laden. So the higher it rises, the cooler it gets because it expands adiabatically, and then it starts condensing, and it condenses. It's pushed up really fast, so it's condensing like crazy. So that's what you get. You also get mature cumulonimbus clouds, clouds that are towering. I mean, clouds that are, they're not the money tails, they're big things. In fact, they're so big, sometimes you see them flattened off at the top because they go so high, they get in the jet stream, and the jet stream lofts them off at the top. So you see these big things, and then you see a streak of them across the top because they went up high enough to get the jet stream. And they're clouds, so they don't have a whole lot of strength in that sense. When they're sitting in the jet stream. And to explain why this happens, like I just did, you get extra credit. And if you have this test, if you have this lesson on a test, and you knew this, good for you. Just saying. Okay. So, and the last one, briefly explain how the airflow aloft aids in the formation of cyclones at the surface. We've spent a reasonable amount of time on this, and so knowing what a cyclone is, what an anticyclone is, know what they do at the surface, what a cyclone at the surface does, what an anticyclone at the surface does, and what the airflow aloft is doing to generate that. Actually, it does three things. It can develop it, it can dissipate it, and it can keep it constant the way it is. It can do those things. So, in both directions, divergent airflow aloft, that's above, and the divergent is going out. So it's sucking up. When it's going out, it's sucking up. So air is being sucked in. So it's divergent at the top, it's convergent, it's being drawn in at the bottom, pulled up, and kicked out. Well, as it's drawn in here, and then drawn up, it's cooling adiabatically, and so you get clouds. You don't necessarily get storms, but you get clouds, and you can get rain, you can get stuff, because there ends up to be a low pressure area there. We've got a cyclone that's talking about low pressure area. That's talking about divergent up top, convergent down below, counterclockwise. It's going counterclockwise. And so that's where up movement is drawn up there. Reducing the surface pressure so you get a low. So anticyclonic is just the opposite. You've got convergent up front. You got air that's coming in and going down, so it's pushing the air from aloft down and out. And it's going out, and that's an anticyclone, and actually that goes clockwise. I mean, I don't know why they did that. It's like they were just making it hard for you that don't care. Well, I mean, it's just, you'd think that a cyclone that would go clockwise and an anticyclone would go the other way, but it doesn't. Sorry for that little injection that probably didn't help anybody. But a cyclone on the surface is characterized by converging air. Converging air, surface winds. This is the northern hemisphere, but that's all I'm going to think about right in this class. So it produced rising air, unstable cloudy conditions, divergent, outflowing fog must continue for it to be maintained. A cyclone does not necessarily mean a twister, as some of you might have assumed. Yes?
So basically, an anticyclone is the exact opposite of a cyclone. So instead of divergence up the top and convergence at the bottom, an anticyclone is convergence at the top and divergence at the bottom.
Absolutely. Yep, that's exactly right. And a cyclone means at the surface, low pressure area. An anticyclone at the surface means high pressure. So if it's high pressure, meaning air is being forced down, it's not rising and cooling adiabatically, it's heating as it's pushed down, so that's why you get clear skies and nice weather. And last night, it was a perfect example. So with the senior class, we went to the gorge and we hiked up Sky Bridge. So we get up there. I mean, it is sweet. The breeze is blowing, nice warm breeze is blowing. The sun is out, in and out, but it's more out. You look out, just sun hitting all those trees, all the different colors of green, just swirling across. So it's really cool. And then we walk down, we hike back and we get to the car and we're going to go to Miguel's. And so we went to Miguel's, but on the way to Miguel's, and the wind was getting, the light summer breeze was getting a little bit harder and a little bit cooler. Because something cool wise was coming against where we were. And pretty soon it was pouring down rain. I mean, in some places we were driving to Miguel's and we went the absolute longest way. We ended up going through not a tunnel. We just went the long way to Miguel's. And it was just like somebody was pouring one of those pictures that you get milk or water or tea and just like, I mean, it was just busted. Then we went to Miguel's and then we went to the Brick. That ice cream. What is it? It was coffee ice cream with pieces of chocolate with a shot of espresso as a milkshake. Oh! Woo-wee. Man, here's a sweet little girl that made it too. I just said, well, I can't put a shot of espresso in there. She said, sure. Now, some people choke up if you ask them to do something a little creative, but she didn't. So, and it cost less. I went there with Elliot. Oh, I don't know if it was a year ago. But anyway, I thought we got hit for about $10 for that thing, but or something. I don't know that I put a shot in, but this was only 8, so I mean, it was worth it for that shit. So, if you like that stuff. Anyway. So, okay, so that's it. That's this. So I mentioned some things that would be good to know, and those would be thunderstorms. So this is part of the thing that you got to hand out of thunderstorms. We've had it. Anybody? Air masses. It came with this. There's a whole bunch of stuff I handed out on thunderstorms. Anybody need a thunderstorm deal?
Oh, this one?
No.
No.
So thunderstorms and lightning, we should. Remember that? That's a whole big pile of stuff. Okay, thunderstorms are localized weather phenomena. So we're not talking about necessarily, we're not talking about fronts anymore. We're talking about something real local. Like we had a downpour the other day, thunderstorm. They're localized. They're in a particular and relatively small area. Weather phenomena that involves thunder, lightning, heavy winds, driving rains, and sometimes hail. So meteorologists estimate that thousands of thunderstorms occur on the Earth every day. And if you're in the plane, I think I mentioned this before, it's really cool to be in a plane at night, looking down at the sky and see thunderstorms happening way down below. If they're happening where you are, it's not as fun. I've never been turned around in a plane where they had to go somewhere else. My wife was. She had to go. She was flying in Cincinnati. They diverted to Louisville because it was just bad. I mean, it was really bad. I've been in anything like that. I can just look down and see them. All thunderstorms start in the same way. They begin with a strong updraft of air, and that would be breathing. You've got an inflow. So what do you have here? It's convergence. You've got convergence here. It's being drawn up. So this is C. The air is being drawn up, and it's drawn up. It cools, and it cools. It condenses, and it gets to a condensation level, apparently pretty low here, and then it begins to condense, and it's still being drawn up, and you're getting a cumulus count. So an updraft is a current of rising air. Usually this updraft is caused by cold front moving in on a warm front. I've talked about this just a minute ago. So you've got a cold front moving in, and there is a slant. This is obviously general. But you've got cold air hugging the ground because it's denser than the warm air. Warm air is not as dense. So this cold air is moving forward, and it can have a slope, and the faster it moves, and I'm not sure, I think it has to do with density, but this angle here that it's cutting through can be steeper or shallower. And if it's really steep, when it hits this warm air here, it's going to kick it up, and it's going to kick it up fast. So it's going to so a lot of moisture is going to be released because it's kicked up past the condensation level, and it's just pushing it up, and so it's just dropping rain like crazy. So you get this fast and intense, and see here the upper level airflow is flattening these up because you're hitting in the jet stream up there. But so it pushes it up quick. It's heavy, thunder, lightning, bad weather, but it doesn't last very long. It's a short duration. If it's more shallow, the slope, and there's not the great difference between the cold and the warm, then it's not going to be so intense and short durated. Okay. The cold air mass tends to get under the warm mass because it's denser, and it lifts it up, making an updraft. Updrafts can occur in other ways, like in mountainous regions, but we were focused on the former. When a strong updraft occurs, the current of air rises, causing it to cool. Air cools, water vapor tends to condense out of the air and clouds. When water condenses, it releases energy, latent heat. Condensation releases energy and warms the surface on which it occurs. In a cloud, the surface is on the little cloud condensation nuclei, little teeny things. So condensation tends to heat up the cloud condensation nuclei. This makes the upward draft even stronger. And when we start talking about even these, like when we talk about that glider, that German glider that flew in, well, there were updrafts and downdrafts of hundreds of miles an hour. I mean, it's really cranking in there. So this makes the updraft even stronger. So condensation releases energy and warms the surface on which it occurs. So you have this condensation nuclei being heated up. This makes the updraft even stronger. As the updraft pulls more and more, a growing cumulus cloud begins to form. So it begins to tower, begins to grow. This is the cumulus stage of the thunderstorm. So there are several stages. There are 5 stages, I believe, of thunderstorm. We're going to cover those in a minute, but that's what he's talking about. The cumulus stage is the development. The cumulus stage lasts usually less than 20 minutes, but the updraft has pushed so much moist air high into the troposphere that a tall cumulus cloud is forming. In the troposphere is where we live. We live in the troposphere. That's where we're breathing and whatnot. So the cumulus clouds can get so tall they actually reach the top of the troposphere, begin to flatten out because of the high winds blowing there. Typically give the cumulonimbus clouds, and cumulo is this growing or heaping cloud. Nimbus is the one that is applied to rain. So that's why these cumulus clouds, there's lots of moisture, it's being kicked up there real quick, and so that's what you get. You get a cloud anvil here. This is the top of the troposphere, roughly, and so you get up and updraft, then you get downdraft. And downdrafts can be people that are flying planes. I mean, there are planes that come into landing and get hit by downdraft, and it can smash them down. It can do bad things to them. I mean, they have things to make adjustments, but they've learned that. So eventually, water droplets or ice crystals in the cloud become too large for the updraft to support. At that point, it begins to rain. This marks the mature stage of the thunderstorm, which consists of heavy rain, thunder, lightning, strong winds, and sometimes hail. As rain falls during the mature stage of thunderstorm, it causes winds to blow downward, hitting the land and spreading out in strong gusts of wind. These downward rushes of air are called downdrafts. These can be quite severe, as winds up to 170 miles an hour have been caused by local downdrafts in the thunderstorm. So here you have warm updraft, and here you have cool downdraft. So you have cold air coming in here, you got warm air pushing up here. Cumulonimbus cloud growing. So as time goes by, typically less than 30 minutes, downdrafts caused by the rain overpower the updrafts. So you have these, as it showed, you have updrafts, you have colder downdrafts, and pretty soon the downdrafts overpower the updrafts, and the start of the storm, and the entire area is full of only downdrafts, and this is the final stage of the thunderbolt, or the dissipation. So 3 stages here: cumulus stage, mature stage, and dissipation stage. And what was just described is a thunderstorm cell. Okay, is it what you have, what I have? So 3 stages: cumulus, that's its building; the mature stage, it's raining; and then the dissipation stage, when the downdraft overpowers the updraft, and then it dissipates. So, like this picture shows, towering begins to build, gets to the highest place it's going to, and then it begins to dissipate. Here's another one. Little example. So it's updrafts here. You've got a mix, updrafts and downdrafts, heavy rain, and then pretty soon downdrafts over. Really, you've got lighter rain, and it's dissipating. Okay. So that is thunderstorms. Kind of quick sweeper promise. There's not a lot that this is lightning. So we had quite a bit of that just the other day. We had a lot of different kind of lightning. And one of the strikes was pretty close. I'd say it was less than a mile. One of the strikes that we had. Now I've heard that for each second it's a mile away. But I watched a couple of things that discounted that. It said, like, I just thought 1,000, but it's more like 5 seconds approximately per mile. About. It's not what I thought it was, but I think about 5 seconds per mile. And this one, the one that hit close, was certainly within less than 5 seconds. I mean, it was a bang. I was working doing interior trim on a big A-frame cedar house in Williamsburg. So it was in the woods, and there were 7-inch high, 3.5 inches wide blocks of cedar with little chisels on the top and the bottom, so they fit together like that. Well, they built an A-frame with a big front, and the front was open. They hadn't put the glass in yet, but the front was open. And so I was putting interior trim around up the side and around the beams and whatnot. So I was just working there, and there was a flash of lightning, and as fast, immediately there was a thunder. I mean, whatever it hit really close. And for 2 hours after that, involuntarily, I couldn't control. Whenever I heard thunder, even if it was like distance thunder, it was so intense. I couldn't control myself. It wasn't that, oh yeah, that's a long way away. I'm glad it didn't hit me. So lightning, an electrical discharge caused by imbalances in positive and negative charges between storm clouds and the ground, or between or within clouds themselves. So you can get within a cloud, you can get lightning within a cloud, you can get lightning between clouds, you can get lightning between the clouds and the ground. And some of this lightning can strike from where the cloud is, it can strike 10 miles away. I mean, you wouldn't even see it coming. Well, you wouldn't see it coming anyway. So, but anyway, it can travel. So during a storm, you have in and out here. You have imbalance between positive and negative charges generated within a cloud. So generated within this cloud, you've got positive and negative charges, and on the ground, then you also have. But generally speaking, the negative charges are hanging low here in the cloud, and positive charges then are on the ground and come to the highest points. I mean, they build up on the highest points. Like that's why you have lightning rods. So a lightning rod is put up there to call the lightning in to strike it, and then if it does right, it'll go down and it'll be stuck in the ground, so it'll dissipate in the ground. And they don't always work. We have one on the chapel that I think twice it's been hit by lightning and it messed up the equipment. So what I don't know why it did that, but it didn't just somehow the lightning rod allowed it to mess around inside. It should have been better than that, but anyway. So colliding particles, rain, ice, or snow increases imbalance and often negatively charge the lower reaches of the storm clouds, while positively charging the upper regions of the clouds. So, these are so long.
Lightning will strike anything that stands high above the ground. Trees are a favorite target. Lightning runs through the trees and stabilizes. A strip of bark can explode like wooden shrapnel and travel outward at lethal speeds.
David Begbie and I were talking about this when he and Sarah hadn't started dating, but they were on the porch and down here when we had a lightning strike that hit a tree up where Miss Griffson, where Andy and Nate are living now. So there was a tree there, and it hit the tree, and it threw chunks of tree out across all. In fact, fortunately, it didn't hit any of the houses, but it shot them across. There were pieces of tree littered over that whole ball field. It just vaporized that stuff. So it's pretty. But some photography here is pretty cool to see. I wonder if in heaven there'll be sound accompanying things. I mean, it'd be nice. Prepare for
We
it.
know what guides lightning's jagged path, or why it chooses to strike in one place rather than another. All we do know is that the path is first created by a trickle of electricity that rushes outward from a charged region high inside the cloud. It begins as a small spark inside the cloud 5 miles up. A spurt of electrons rushes outward, travels 100 meters, then stops and pools for a few millionths of a second. Then the stream lurches off in a different direction, pools again and again. Often the stream branches and splits. This is not a lightning bolt yet. It's called a stepped leader, an intensely charged channel leaping and branching down. gets close, its electric field begins to exert a pull on the ground.
When that step leader is within 10 or 100 meters of the ground is now aware of there being a big surplus of negative electricity, which has come down on a conductor. Certain objects on the Earth respond by launching little streamers up toward the step leader. Weakly luminous plasma filaments, which are trying to connect with what's coming down. If you happen to be standing there, maybe a streamer is going to leave your head and head toward that step leader. A telephone pole might launch a positive streamer. A blade of grass might launch a positive streamer up toward the step leader. It's that special one which makes the connection, which gives rise to the return stroke, and then this catastrophic 10,000 ampere current flows. That closes the switch.
When that connection is made, the electrons drain to Earth in a blinding bolt of light. The part of the channel nearest the ground will drain first, then successively higher parts, and finally the charge from the cloud itself. So the visible lightning bolt moves up from ground to cloud as the massive electric currents flow down. These positive streamers only exist for a minute fraction of a second. Photographs of them are extremely rare. Here, 2 streamers left the treetop, but only one of them successfully connected with the descending step leader. A nearby telephone pole also launched a positive streamer upward, a fatal lightning bolt.
So if you feel your hair is starting to stand up on air, you need to get down. Yeah, I don't know that you'd run. I'd go down.
Decades, ordinary pilots have also reported seeing brief flashes in the sky above storm.
Mr. Whistler will probably just have to go by intuition.
But perhaps they were true. This research footage was taken above the massive lightning storms of the American prairies. Scientists have nicknamed these flashes sprites. They're almost too faint to be visible and last a fraction of a second. They're 10 miles wide and reach over 50 miles straight up from the top of the storm. Nobody yet knows what they are or how the storm creates them. Their power and their effect on the atmosphere are still mysteries. But you need to go higher than a plane can fly before you can appreciate the real scale of lightning on Earth. Images from a low light level camera on the space shuttle show nighttime storms flickering across entire continents.
These 100% graphs of these 6 from Haley Valley are 30.
Whoa. 36 bucks. Wow, that's crazy. That's a terrible deal.
Now this is very simplistic, and there might be a lot of commercials in it. At least when I watched it before, there were.
I'll react to every single one.
Hmm?
I'll react to every single one of the ads.
Now we'll talk about lightning. You see some clouds here. What you're seeing is really just the bottom edge of some clouds. Thunderclouds can really be very, very tall, several miles high in many cases. And weather inside the clouds, with the movement of air, usually up and down, can cause charge inside the cloud. You get a buildup of charge, positive charge, for example, at the top of the cloud, and negative charge down at the bottom. So I'll draw some negative charges here, representing a bunch of electrons built up on the bottom edge of these clouds. And again, this is happening because of weather inside the cloud, movement of air inside the cloud. The cloud has basically become polarized with the positive charge up on the top and negative charge down on the bottom. Now let's draw the ground down here. And we'll put some water over here. And let's put some structures down here. Here's a little house. And we'll put a tree next to it. Leaves on it. And let's put a car down here, parked next to the house. Okay, a couple other things. We'll put a person out here. Let's put a boat in the water. And this guy shouldn't be out sailing in the storm, obviously.
Challenge accepted.
Okay. The negative charge on those clouds has an effect on the ground beneath it. Remember we talked about charging by induction. The same thing happens here. On the ground, there are positive charges and negative charges. And the positive charges are from the protons, which are stuck in the nuclei of the atoms. The negative charges, the electrons, are much more easily moved, and they're repelled by all the electrons in the clouds. So these electrons tend to get pushed away. They get pushed deeper into the ground or spread out by the negative charge in the cloud above. So the ground beneath now has been charged by induction. The ground is positively charged. And all the things on the ground are positively charged. The tree gets positively charged. The house gets positively charged. The car, even a little bit. The electrons don't really move out of the car very easily because the car is sitting on rubber tires. And the electrons don't flow through the tires very easily. So the car probably won't develop that much positive charge. But the person on the ground will develop some positive charge too. Now, when something is charged, the charge tends to concentrate on the corners and the pointy parts of an object. So it's going to be the corners of the house up here and the treetops, the tips of the limbs that develop a lot of positive charge. This is also going on in the water over here. Electrons are repelled through the water and the boat becomes positively charged, and the tip of the mast up here in particular becomes very strongly charged, all the little pointy parts. And if you're out in open land, this is a large flat area, and you are the one thing sticking up. You are essentially the pointy thing, and a large positive charge will develop on you. Anything sticking up relative to its surroundings will be more strongly charged. Now the electrons in the cloud are negative, and they're attracted to the positive objects on the ground. And if the force of attraction is strong enough, the electrons will jump across the gap, and that is a lightning bolt. These electrons
Shocking.
come flying down, and each of these is a lightning strike. Globally, around the world, there are approximately 100 lightning strikes per second. And you might think, well, I don't hear a storm at all right now, but somewhere there's a storm. Probably in lots of places right now there are storms. There are some places down off the coast of South America that get about 7 days of sunshine a year. They're just massive storms. Some of these are over the ocean, some are over land, but there's about 100 lightning strikes per second. That makes lightning the number 2 cause weather-related death. Flooding is the most common cause of weather-related deaths. Lightning is the second. And a lot of times there's multiple lightning strikes in a single stroke. When lightning strikes, you might see a flash, you might see this bolt flicker. There's several strikes at once right through the same place. And it makes an electrical disturbance that you can actually pick up on AM radio. It will just sound like static on AM radio. If you're driving in your car and there's a thunderstorm, not even over you, but just anywhere nearby, and you're listening to AM radio, you can hear a little static, a burst of static on the radio every time a lightning bolt strikes. And lightning can also travel from ground to cloud as well as from cloud to ground. And it can also travel from one cloud to another. If there's a positive region on one cloud, say this cloud is polarized this way, the negative charge is built up over here, you could get a lightning strike from one cloud to another. You can also get a lightning strike within a cloud. And what people call heat lightning is really just a regular lightning bolt. You might have lightning that's really far away, too far away for the thunder to be heard. And often you see the light reflected off the clouds or the glow of the light through other clouds between it and you. But there's a lightning bolt in there that's causing the glow. So what people refer to as heat lightning is typically just regular lightning. Now, in addition to striking these areas where the positive charge is concentrated, that's obviously the best choice for a target. Lightning's attracted, the negative electrons are attracted to the positive charge, so it's going to go toward the places where the positive charge is most strongly concentrated. But there's another thing going on as well. Lightning seeks the easiest route to the ground. And just as water doesn't flow straight down a hill, it will wind down the hill, finding the easiest route to the ground. The lightning winds through the air, and that's why you see the bolts aren't perfectly straight. The atmosphere, you can't see it, but there's different pockets of air, different density, and different temperature, and different humidity. And the lightning is winding its way through that, finding the easiest route to the ground. When the lightning comes over here to the tree, for example, it's going to go through the tree rather than beside the tree. Even though the wood isn't a good conductor, it's a better conductor than the air over here. So the lightning, seeking the easiest route to the ground, will go through the tree. And all this negative charge is then dispersed through the ground and neutralizes the positive charge in that region. But it seeks the easiest route to the ground. And you, if you're standing out here, you are a better conductor than the air around you. So the lightning will prefer to go through you rather than beside you. And you don't necessarily want to stand next to a tree seeking shelter either. If there's a tree over here and you're trying to get out of the rain and the storm, remember the tree's a good target for lightning. And this tree will be positively charged, and lightning will be more likely to strike the tree than the ground next to it at a safe distance. And if lightning strikes a tree very close to you, it can still be deadly. Even if it doesn't hit you directly, it can still kill you. And there are stories of people getting killed in situations like this. Golfers, for example, out in the middle of a golf course and a storm comes up, and so they go hang out under a tree waiting for the storm to pass. Lightning strikes the tree, and people have died on golf courses from that situation. A car, though, is pretty safe. It's a pretty safe place to be inside a car. And it's not really so much because of the rubber tires. Lightning could still strike a car. But in seeking the easiest route to the ground, lightning's going to go through the metal exterior of the car, because metal is a very good conductor. And so the lightning could go through the metal of the car and then jump to the ground, leaving the occupants of the car untouched. So you're really pretty safe inside a car from lightning, even if lightning were to strike the car, which isn't as likely as striking something sticking up much higher. But even if it were, you're still safe inside the car. Because lightning always seeks the easiest route to the ground, you can actually trigger lightning. And scientists...
This one I won't go through, but they talk about lightning rods and how there are people, when this was put out, there were still people that are going around and telling people that have lightning rods they need to be adjusted. So they adjust them. So they have tools, they go up on the road They don't do anything with it. I mean, lightning rod is a lightning rod. Doesn't need any adjustment. But they've scammed people, and still probably are scamming people with lightning rods, saying they're lightning rod adjusters. And for $50 they'll go up and adjust your lightning rod. So it'll work.
It's like having somebody walk your goldfish for $50.
That's right. That's right.
What do you use the walk to?
So you want to be, that's the whole point of this class. You want to be able to see through these arguments that are foolish. Okay, well, objects on the ground, as we've just heard, like steeples, trees, and the earth itself become positively charged, creating an imbalance. And then that nature seeks to remedy balance by passing current between the two charges. So, and now he didn't mention the step leader and a stringer here. He didn't mention that usually from the object that's high will come off something here that this will come down and they'll meet, and then you'll get a transference. So cloud to cloud, cloud to ground, lightning bolt, negative charges race down about 200,000 miles an hour along a channel called a steep leader. Not a steep ladder, but a steep leader. That's this one here. A steep leader is a channel of negatively charged particles originating from the bottom of the cloud. So these negatively charged. Now this has become is moving up this way, but this is coming down. This is a step leader. The step leader. You saw where the house was and the telephone pole, and the house had two little pieces coming off here, and the telephone pole. Well, this lightning came down and just took the one in that tree. Well, that was a step leader coming down, and it extends about 150 feet toward the earth. As the leader nears the ground, it's met by streamers, and that little thing coming up from the tree in the photograph, coming up from the tree or the house, wherever it comes from, the telephone pole, was a streamer, and that streamer then the lightning bolt, the step leader chooses. I don't know why, how it decides on the choice, but it makes a choice as far as to which streamer to hit when it's got an opportunity to choose. And then the two connect, the steep leader and the streamer, and electric current flows as negative charges fly down the channel toward the earth. A visible flash of lightning streaks upward at 200 million miles per hour. Now it looks like it goes down. I mean, when I watch these things, it looks like it goes down. But they say that it goes up. And it goes up really fast. It comes down, it's coming down at 200,000 miles per hour. But it goes back up at 200 million. And each bolt of lightning can heat the air around it to over 50,000 degrees Fahrenheit. That's where we get thunder. The thunder comes, if you don't have lightning, you don't have thunder. And you can have thunder and not see lightning because it's so far away. But it heats the air immediately. I mean, if it's going 200 million miles an hour and it's this hot, air is immediately expanding. It heats, it expands immediately faster than I just did. And so then you get the rolling business. So the return stroke in lightning causes the booming sound we call thunder. It's a return stroke, it's going back up. That's the thing that is going so fast and superheating the air. Causes it quickly to rush outward in waves, forming sound waves that are easily detected as thunder. Lightning strikes the earth, every surface, about 100 times every single second. Okay. I will see you Monday.